So I think in grade 11, we sometimes just referred to these as the big five. So these are the big five constant acceleration equations, right? So if you have motion of some sort, but you have constant acceleration, I guess if you want to, you can include acceleration equal to zero because these will all work out too. Then you can use any of these. So this here I will call equation. Well, let's just. I feel like I should number these. I should have maybe before, but we'll call out equation 1, 2, 3, 4, and 5. So where does equation 1 come from? You could look at this as kind of just you taking the average velocity and multiplying by the time, right? If you remember if you rearrange the equation, right, d equals vt, right? That's going to give you your distance if you just take the equation for velocity. And then what you're essentially doing here is you're saying, oh yeah, I do have a velocity that's changing, so I'll just take the average because I have constant acceleration, right? That sort of works out. So that's one way to think of it. I usually try to remember this as kind of the I don't know if that's going to work for me. Yep, as the graph one. So if you have let's say you've got v1 and here you've got v2, t1, t2, and you've got something that's changing like this, and you want to know from T1 to T2, how far does it go? Well, do remember that displacement, right, is area under the curve. And so the way you would kind of take that, right, you'd be saying, I need to get the area between T1 and T2, right? I need to get all this area here. And the way to do that, or a nice way to do that, is just to say, okay, well, I'll just take the average velocity between these two. And so that works out to be the same area here. And you can also see from this why it's important that we have a constant acceleration, because then we can just take the average of the two. Our second equation here, v2 equals v1 plus at. This is just the definition of acceleration, right? If you start with the idea that acceleration equals delta v, which is v2 minus v1 over t, right? Multiply both sides by t, that gives you at. And then add v1 to both sides. You could alternatively, if you wanted to, right, you could go from there to here. Or you can even rearrange this for v1 instead, right? You could add v1 to both sides, but then subtract at. So you could say v1 equals v2 minus at. You could go either way, but usually this is sort of the one we give you because often v2 is the one that you want, right? You're given an initial speed or velocity. I'll kind of use them interchangeably because for these equations, you could just use them for speed or distance. If it was velocity or whatever, you could break it into components and just use them that way. So I'll just kind of use them interchangeably here. But yeah, you could use that either way and figure that out. The third one, if memory serves, just take equation 2 and sub it into 1. Right? So since equation 2 is in terms of v2, then you can say that means d equals v1 plus V2, but for V2, use V1 plus AT divided by 2 and times by T. So you can see how I took V2, which is in equation 2, and just where there's a V2 here, I just substituted in V1 plus AT. And then if you work that out a little bit, that means that D equals, well, you can see how I've got V1 plus V1 in there. So that becomes 2V1 plus AT. And you could, I guess you could leave that over 2 if you want. Since this whole thing is times by time, you can multiply that through. So that's breaking this apart a little bit more. You can see for the first one, it cancels out, and that leaves you with that exact equation. So D equals, the 2 over 2 cancels, which just leaves you with V1T plus, we usually write it that way, but you could leave it as AT squared over 2, but we usually write 1/2 AT squared. And that's that equation. So just a little bit of math. Equation 4, let me call this equation over here, let me call this 2b, since it's just another version of that. So for number 4, I'll leave this as an exercise, but if you wanted to get equation 4, you can see how it's very similar to equation 3. It's just got V2 instead of V1. So if you wanted to get this one, you would just sub 2b into equation 1. And you should be able to derive equation 4. So I'll let you do that on your own because I don't want to have all the fun. And for the last one, I think you need, I need a 3C. So if you go back to equation 1, you can see how we've got time here. So we've got V1 plus V2 over 2T. So basically, we just need something to substitute in here for T. So you take equation 2 and rearrange it for time. So I could also here, right, you can see here, I'll just say, or I could basically swap the A and the T here, right? Just multiply both sides of this equation by T, divide both sides of this equation by acceleration. So the acceleration cancels and it leaves you with T equals V2 minus V1 over A, if you wanted to rearrange that equation for time. And I guess I will call that 2C. And then you substitute that. So equation 1, remember, was D equals V1 plus V2 over 2. And time, we just said, is V2 minus V1 over A. So you multiply these together. Now the key, if you're doing a multiplication like this, is remember these are technically, right, binomials, right? This is V1 plus V2. You have to multiply the whole thing. So go back to grade 10 when you learned FOIL, and that just means you have to multiply everything by everything. So that means D on the top would be V1 V2 minus V1 times V1, which is V1 squared, plus V2 squared, and then minus V2 V1 all over 2A. Then you'll note that I've got V1 V2 minus V2 V1, which is the same thing. The order doesn't really matter. And that gets us our lovely equation, which is d equals v2 squared minus v1 squared over 2a. And then we ask ourselves, why did we do all this math? Aside from the fact that we enjoy math and it's fun, and we've got 5 different equations now, why do we do all this? What's the point of it? Yeah, it's actually to make your life easier, because depending on the information you've got, right? Um, if you look at like this last equation, maybe I give you an equation where I don't give you the time, right? So you could do a multi-step process where you go up and find one of these equations, like equation 2, solve for time, then you go down to an equation like equation 5, and then solve for the distance, right? So if you have these handy, it can actually save you some time. If you look at like, what are all the variables here, right? All variables. So we're looking here, well, obviously we've got a d, we've got v1, we've got v2, we've got the acceleration, and we've got time. These are all the things that are involved in these constant acceleration problems. So if you look at what I like to say, what's not there? And you look at equation 1, right? What's missing, right? There's no a, right? There's no a term here. If you look at equation 2, you can see there's no d there, right? And if you look at equation 3, you'll notice there's no v2 or v final, however you happen to write it. And then equation 4, in kind of a parallel, there's no v1. And finally, for equation 5, right, there's no time. So if you're solving problems like this, usually what's going to happen is you're going to be given 3 pieces of information and you're going to want the 4th one, right? And so if you know all 5 of these equations, or you've got them handy, then you can just pick the right one and get what you want in one step, as opposed to having to go through multiple steps and solving stuff. So it's very handy to have these. It's a nice time saver. Often will, actually in the textbook will kind of go through that process where they'll list the information you have, state the information you want, or the variable in this case that you want, and then it's basically just match it with which of these 5 equations gives you the thing that you want, right? Has all 4 things that you want, and then you can avoid that other thing. So I will try to demonstrate this if I can. Speeding along in a car, Carl passes Mr. Brown at 72 kilometers an hour, which remains constant. That instant, Mr. Brown starts running from rest, accelerating at a rate of 4 meters per second squared. How long does it take Mr. Brown to pass Carl? Right? So we've got someone driving at a constant speed, right? So we can say, here's kind of our starting point, right? And we've got, I guess we could say, v of Carl here, which is a constant. Now it's 72. Notice here, I've got meters per second and other stuff. So 72 kilometers an hour, I would convert that. So the conversion factor is just 3.6. And you want the simple one. So if you take a number in kilometers an hour, divide by 3.6, and that should give you, in this case, 20 meters per second. If you want to go the other way, multiply by 3.6. And that's just because there's 3,600 seconds in an hour, but there's also 1,000 meters in a kilometer. So if you just go through those 2 steps, you can get the same answer. But I always just try to remember that the conversion factor is 3.6, and kind of helps out. Also convenient if you're trying to think about how fast is that in kilometers an hour or something like that. So in this case, for Carl here, we've got 20 meters per second, and that's constant. Now, for me, which we'll go with, so for me, I start out at rest and I accelerate, right? So for right, we've got V1, or call it VB1 or something if you wanted, but V1 is 0. And what else do we know about what's going on here? We know the acceleration is 4 meters per second squared. That's about it. That's about all we really know. And in the other case, when we look at the car here, or Carl, we know the acceleration is 0, right? It's moving at a constant speed. And that's about it. Starts at the same time. If we wanted to, for this case, though, we could look at, well, how far, right, is this car going at any particular moment in time? And we know that for a constant speed, it's just VT. So that means the position at any point relative to where we started, or the distance traveled here, is just going to be 20t. Now, is this helpful? Does that get me anywhere? I guess the question I really want to say is like, okay, I've got two different actors in this, right? I've got a car and I've got, well, myself, I guess, running very fast as I do, or eventually. But how do I really solve this? Like, what needs to be true for the question asks for how long it takes to pass? So essentially, then I want to know at what point do I catch up with this car? What has to be true when I catch the car? Yeah, absolutely. Right. The positions have to be the same. Right. So we're starting at the same. This situation starts right when the car passes me. So we're at the same position then. We want to know when, at what point later in time are we at the same position. So that's the real key here, is that our positions, or the distance traveled, has to be the same. So what about for me? Well, for me, I'll just do DMB. I guess we could say here D is for the car or something. What would mine be? And here's where, like, knowing some of these equations can help a little bit. I definitely don't know V final, and I want to avoid that. Right, so I want the equation that doesn't have that in there, so I can use V1t plus 1 half a t squared. Now note that V1 is 0 to start, so that whole first term just cancels out, and that leaves me with the acceleration is 4, so 1 half of 4 is 2, so that just gives me 2t squared. Right, and now when I catch the car, right, just to be really clear about this, right, my distance is equal to the distance the car has gone. And so that means I can take those two equations and just set them equal to each other, right? Which means 2t squared must equal 20t. I can divide both sides of this equation by 2t, because I can do anything I want. That's just math, right? Anything you want to one side of an equation, as long as you do the same to both sides. So let's divide by 2t and divide by 2t. One of the t's cancels out, so that just leaves me with a t on this side. And 20 divided by 2 is 10. And the other t's cancel. So that tells me this happens at 10 seconds. And what's really, really nice is that's what the question asks for. So one tip for any time you're answering these questions, you get an answer, even if you're not sure if you're right, or you think you finished it, go back, read the question, make sure you've answered it. In this case, I have, right? I'll say overtake the car. So yeah, so anyway, this is kind of a general example, but probably the most important part about it is when you get something like this, asking yourself what has to be true when I get my solution, right? In this case, the distances have to be the same and the times have to be the same. So I might have rearranged these equations for time, but then when I set them equal to each other, I would have gotten a solution for distance. So this was actually worked out the better way to sort of do it. Okay, so these are, like I said, this is a conceptual example I have here. Two astronauts far out in space, which I like because that just gets you away from everything. You can just imagine like two people out in the blackness of space, far, far away from anything else. They're traveling 2 times 10 to the 6 meters per second, so 2 million meters per second. That's pretty good. Side by side. Astronaut B starts to accelerate at a rate of 8 times 10 to the 5, so 800,000 meters per second to the left. How does this motion appear to astronaut A? So I can, just for something to look at or whatever, we can say, well, they're going forward, whatever that is. So um, B goes to plus. So that means, so I would situate this something like this. So we've got um, astronaut A, and right beside we've got astronaut B. They're going through space together. Right, same V's, same velocity here. And this is 2 times. And then B starts, so later or whatever. We've got B starts to accelerate 8 times 10 to the. That's about the best I can try to represent the situation or what's happening here. So, yeah, so how would this appear to astronaut A? All right, so it looks like a mixed opinion. Um, in reality, though, if you were astronaut A, this motion would appear to the left, right? Purely to the left. That's all you would see. Um, and you could kind of think of it like if you wanted to, right? You could say, well, A's, if you wanted to look at A's motion, right? A is going like this, and um, B still has this same forward component, right? So they are both traveling initially at 2 million meters per second, right? That's not changed. B is only accelerating to the left. So B's forward velocity, if you will, is preserved. There's nothing to affect that. So it's completely preserved. So if you looked at that component of its velocity, B is still moving forward at the same rate. Now, since A has no other reference frame, right, as far as A and B, and here's another thing to think about. Initially, when this starts, do A and B even really think they're moving? Right? Yeah, they're out in space, but if everything else is really, really, really far away, to them, they're not even really moving, right? They might as well be stationary out in space. It's just we're saying that they're moving 2 million meters per second, but relative to what, right? So as far as they're concerned, like they're stationary. A and B are just beside each other. They're not accelerating, so they're not feeling any force. They're just floating in space. Then B starts accelerating to the left. So, that's where that motion comes from. And so from B's perspective, like B would, if you were drawing it, would look like that, because B would start getting faster and faster to the left. But from A, it would look like B is just going directly away. Okay, another one. Flying 120 meters per second west in a rocket pack. Jalisa accelerates at 30 meters per second, north 30 degrees east for 10 seconds. What is Jalisa's final velocity? I feel like this one is more consistent with just what we've been looking at, right, with the big five questions and all that. So this seems like one that might be good for you to give a little bit of a try, and then we can go over it. Okay, so for this problem, we have someone in a rocket pack, which seems pretty cool. They're going 120 meters per second west. Okay, and then they accelerate 30 meters per second squared north 30 east for 10 seconds. We want the final velocity. So, what I did first is I took the acceleration and broke it into components. I said, look, I need to look at the x component and y component separately for problems like this. So just doing that, I just sketched out that vector here and wrote in the 30. You can see here's the actual acceleration vector. When you break that into components to get the x component, I just, again, I sometimes write out stuff like this just to make sure I get it right. So I say, okay, I know the sine of 30 is the opposite side, which is what I want, the x component here divided by 30, rearrange it, and then I get this. Now sine of 30 is 1/2, so that works out to just be 30 times a half. And then I do basically the same process for the y component. I do the cosine of 30 is what I want, this y component over 30, rearrange that. Cos of 30, what is it, like 0.86 or whatever, or root 2 over 3. Or, yeah. So, I'm losing my mind. So once I get the components of this, then I can look at each direction completely independently. A wonderful thing about doing problems like this, you can always look at x and y all by themselves. So just in the x direction, right? I can look at the information I have. I know the initial velocity is 120 meters per second because she's going initially completely in the west direction, which I said east is positive, so that makes that negative. The acceleration is 15 because that's what I found up here. That's the x component of the acceleration. Time is 10 seconds, and then what I want is v2. Technically, v2 in the x direction. So then I look at those big five equations, which one is most useful right now? And that's v2 equals v1 plus at. Substitute in those numbers, negative 120 for v1 and 15 for the acceleration, 10 for the time. And that works out to, well, negative 120 plus 150 is 30. And I just stuck a little x here for the velocity just to be very clear. This is the x component of v2. I didn't write it much before that because I'm being a bit lazy. And then I can look at the y dimension independently all by itself. Initially, she's traveling just to the west. So the y, which is the north-south direction, has a velocity of 0 initially, but is accelerating at 26 meters per second squared in that direction. I know I left off the units there, but sometimes it's helpful to put the units just to make sure you didn't get something in kilometers an hour or something like that. And again, we want V2. Use the same equation. On this case, V1 is 0, so it's just 10 times 26 or 260. And that's enough. Now that I know the x component and y component of the velocity, that's enough. I can sketch this lovely vector here. Again, the sketch is so important. I can say I know it's positive 30, which is toward the east, and I know it's positive 260 in my coordinate system. That means I can make this vector here. And then when I draw in this angle, this theta, I know that angle means I have to start out east and then go toward the north, right? So that's how I'm going to report that angle when I get it. And then it's just, I've got a triangle. It's just do the trigonometry here. Calculate the magnitude of that velocity. That's just Pythagorean theorem, right? Just the square root of 30 squared plus 26 squared. And then to get the angle here, set it up. I usually write it out this way. I know the tangent of that angle is the opposite side, 260 over 30. And then I get that angle, write it out, and you're done.